Hello everyone. So today I'm back with a new video. So today I'll post a lecture on the thermodynamics series which I was continuing. Please do watch my previous videos, lecture 1, 2 and 3 to get an idea about the thermodynamics first law, zeroth law and the fundamentals, the common fundamental terminologies used in thermodynamics. Please do watch my previous videos on that. So let's start today's lecture. Let me share the screen. So I was discussing about the internal energy. If you remember, if you do not remember, please watch my previous video on internal energy of the system. So what is that? Internal energy is the energy possessed by a system by virtue of its existence. Okay, I've discussed in detail on that. Please do watch my previous video on that. So we denote internal energy as U. So this is a function of temperature and volume, if you remember. So what is the mathematical formulation of du? du equals to ncv dt for n moles of ideal gas. Okay, so cv is the heat capacity at constant volume. Okay, and this is valid for ideal gas uh, situation. So you must have known about ideal gas. I will make a separate series on the gas, so I'll do that, but I hope you know about ideal gas and VanderWaals gas. Okay, so I can briefly tell that there is no intermolecular attraction present within an ideal gas. Okay, and obviously, you must have known about the VanderWaals gas, the gases which obeys VanderWaals equation. So for that, du equals to ncv dt plus an square by v square. So this is the term for du for n moles of VanderWaals gas. Okay, like gas is a real gas which obeys VanderWaals gas equation. So A is a VanderWaals constant. So this is the terminology of du for that. Obviously, these two are valid when there is no phase change or chemical transformation occurring. Okay, so no phase change or no chemical transformation occurring in this scenario. These two is the expression of du in case of ideal gas and van der Waals gas. Okay, and now let me quickly switch to the mathematical formulation of the first law. I have derived the first law in my very first lecture, I believe. Please do watch that. So I will not derive it here. I will just write the expression which I have already derived in my first lecture. So this is the mathematical uh, formulation for the first law of thermodynamics. That is Q equals to ncv dt plus P plus del U del V T dV. So this is the mathematical formulation of thermodynamics first law. I had derived it in my first lecture. Please do watch that. So I'm picking up the mathematical form from there. Obviously, you know N is the N mole of gas, CV is the constant volume heat capacity. Okay, you know all the terms. So for I will quickly discuss some of the formulations of first law of thermodynamics in different type of process and for ideal gas and for real gas. Okay, so for ideal gas, what do we know? That there is no intramolecular interaction present within the system. So internal energy, it will not depend on the volume change of the system. Okay, because there is no intramolecular interaction present within the system, so internal energy, it will not depend on the volume change of the system. Okay, so in that case, del U del V T equals to be 0 because U is independent of the volume change. Okay, so for ideal gas, what will be the first law, mathematical form of first law? It will be Q equals to mCV dt plus PdV. So this is the first law, mathematical form of first law for ideal gas. Okay, if uh, 1 mole of gas is being used, then it will be Q equals to CV dt plus PdV. Okay, so for real gas, which obeys VanderWaals equation, real gas which obeys VanderWaals gas equation, what will be the mathematical formulation of first law? I have already discussed in my previous slide what is the uh, formulation for du. So del u del v t, it will be equal to an square by v square. So in that case, the first law will be Qu equals to, if you remember, Cv dt plus P plus del U del Vt dV. So I'll just put the value of del U del Vt over there. So I'm writing it here so that you can understand. Cv dt plus P plus del U del Vt dV. So I'm only putting this value over here. So Q equals to CV dt. I'm writing N for N moles of gas plus P plus AN square by V square into dV. So this is the mathematical formulation of first law for real gas. Okay. So now I'll quickly discuss some special cases, some typical processes, the mathematical formulation of first law of thermodynamics in case of some typical process. Okay, so let's first start with cyclic process. If you do not know about the process and the types of different process, please do watch my previous videos on that. I have discussed everything in details. What is a thermodynamic process? Which are different types of process? Please do watch that. Okay. So for cyclic process, a state variable it comes back to its original state after a number of series of things. It comes back to its original state. So uh, in this case, the internal energy change that will be zero, because u is a state function. I have already discussed about state function. Okay, so this is the property of state function, that in cyclic process difference in the change of the state function will be zero. So u is a state function, internal energy change, so it will be zero. So what is the first law? Q equals to du plus w. So du equals to 0, that means q equals to w. Okay, this is valid for cyclic process. So heat is being completely converted to work. Okay, so next, this is the first law. And next, for isothermal process, what will be the first law mathematical interpretation? So if you remember, for isothermal process, uh, temperature is constant. That means dt equals to 0, because temperature is constant. So in this case, q, we already know that q equals to ncv dt plus w. This is the first law. So what is ncv dt? This is for the expression of du. Please remember, I am deriving all of this process for considering a gas to be ideal. This is not a case of real gas. Okay, so this will be equal to ncv dt plus w. So if dt is equals to 0, in this case also q equals to w. Okay, so again heat is being converted to work completely. Okay, and next I will discuss about adiabatic process. If you do not remember what is adiabatic process, please do watch my previous videos. In this case, no exchange of mass and energy is being allowed between system and surroundings. Okay, that is a adiabatic process, and it occurs within an isolated system. So in this case, no heat exchange is allowed between the system and the surroundings. So q is equals to 0. So what will be the first law then? 0 equals to du plus w, or w is equals to minus du. So this is the formulation of mathematical formulation of first law. So what this suggests, that whenever a system works in an adiabatic process, the internal energy will decrease. That is, the system works on expense of its own internal energy. Okay, so this is the expression of first law in case of adiabatic process. So considering the ideal gas, du is equals to cv dt, considering 1 mole of ideal gas equals to cv. This is the change in temperature. I'm writing this as T2 minus T1. So this will be W equals to CV T1 minus T2. I'm just putting it over here. Okay. So if we restrict the work to be mechanical work only, if the work is only mechanical work, what do we know? W equals to PdV. So in this case, it will be PdV, that means P into change in volume, V2 minus V1 equals to CV T1 minus T2. Okay, so this is the mathematical formulation of first law in case of adiabatic process. So for adiabatic expansion of gas, if the gas is expanding, in this case V2 will be greater than V1. So in that case T1 will be greater than T2. And if V2 is less than V1, T1 will be less than, I'm sorry for this, uh, yeah, so T1 will be less than T2. Okay, so for adiabatic expansion of a gas, the temperature will fall down, and for adiabatic compression of a gas, the temperature will increase. Okay, so this please remember this for an adiabatic process. For adiabatic expansion, this is for expansion because V2 is greater than V1. In this case, T1 will be greater than T2. That means there will be a fall in temperature. And for compression, if the gas is compressing, that is V2 is less than V1, in that case T1 will be less than T2. That means there will be an increase in temperature. Okay, so let's go to another process, that is Horrid process. I have also discussed about it in my previous lectures. So in this case, volume is constant. That means dV equals to 0. So what was the first law? The first law was W equals to, uh, in this case, if dV is 0 and we restrict the work to be mechanical work only, then W is equals to PdV, then W is equals to 0. Okay. So Q is equals to du. This is the formulation of first law for an isochoric process. Here no work is done and the total heat supplied increases the internal energy of the system. Okay. I hope you have understood all of these first law formulations for different process and for ideal gas and real gas. So now we will derive the relation between the state variables for an ideal gas considering a reversible adiabatic process. So let me write this. Relation between the state variables. What is state variables? Temperature, pressure, volume, and mole number for an ideal gas considering a reversible adiabatic process. Okay. So we will derive the relation between the state variables, temperature, pressure, volume for an ideal gas considering reversible adiabatic process. So I will derive the relations step by step. The relation between T and P, uh, T and P, and also P and V. So I'll do this step by step. So let's get started. First, let's try to derive the relation between T and V, temperature and volume. Okay. So what do we know for reversible adiabatic process, which just now I had written over here, the reversible adiabatic process, P into V2 negative V1 equals to CV T1 minus T2. Okay, I can even start from the beginning. So Q is equals to 0 for reversible adiabatic process. Q is equals to 0 as there is no heat exchange between the system and the surroundings. So the first law says that 0 will be equal to CV dt plus P dV. This is Q equals to du plus W. I am only putting the terms. Q is equals to 0 for reversible adiabatic process, and du is equals to Cv dt in case of ideal gas, and W equals to Pdv if we restrict our work to be mechanical work only. Okay, so now we know from the gas equation, for ideal gas equation of 1 mole gas, Pp equals to RT. We know that, so P equals to RT by P. So we can put this value of P over here in this equation. So it will give us 0 equal to Cv dt plus RT by V dV. Okay. Now I am transferring the terms over here. So negative Cv dt equals to RT by V dV. Okay. Now let me integrate it. So I am putting Cv dt by T. I am just keeping this T over here and putting this RdPV by V. Okay. So now let's integrate this in both sides, T1 to T2, and this will be similarly V1 to V2. So what will be this integration? Negative Cv ln T2 by T1 equals to R ln V2 by V1. Okay, so we can considering reversing this sign. So Cv ln T1 by T2 equals to R ln V2 by V1. Okay, let me go to the next page. So where was I? Cv ln T1 by T2. Let me write this again. Cv ln T1 by T2 equals to R ln V2 by V1. R ln V2 by V1. Okay, or ln T1 by T2 equals to R by Cv ln V2 by V1. So what is R? We know R equals to Cp minus Cv, okay, by Cv into ln V2 by V1. So we can just raise this to the power. This is the a formula from the ln log. If you remember the basic mathematics, so ln it will be equals to V2 by V1 to the power Cp minus Cv by Cv. Now what is this Cp by Cv? We know that Cp by Cv equals to R, equals to gamma. We all know that, okay? Let me write this. Cp minus Cv by Cv. This is equals to Cp by Cv minus 1. We know this is equals to gamma, so it will be gamma negative 1. So I'm just coming back over here. Ln T1 by T2 equals to ln V2 by V1 to the power gamma minus 1. Okay, so we can write it from here. T1 by T2 equals to V2 by V1 to the power gamma minus 1. So this is the the relation between T and V. T1 T1 V1 to the power gamma negative 1 is equals to T2 V2 to the power gamma minus 1. So this is the relation between temperature and volume, or we can write In short, Tv to the power gamma minus 1 equals to constant. Okay, so this is the relation between temperature and volume in case of an ideal gas in reversible adiabatic process. So this is a very important relation. I have derived this. Next, go to the relation between P and V. Okay, relation between P and V. So similar thing we already known that Q equals to 0 for an adiabatic process. So 0 will be equals to CV dt plus P dV. So we know PV equals to RT. This is the ideal gas equation. So if I do a partial derivative, it will be PdV plus VdP equals to RdT. So what we can write for PdV? PdV will be RdT minus VdP. Okay, so now I'll put this over here. So 0 is equal to CV by R into PdV plus CV by R into VdP plus PdV. Okay, so now we can write CV by R plus 1 into PdV plus CV by R into VdP. Okay, then what is this CV? So CV by R plus 1, this will be CV. I am just doing the addition, plus R by R into PdV plus CV by R into VdP. Okay, so what is this? CV plus R, this is equals to CP by R into PdV plus CV by R into PdP. Okay, so let's go to the, oh, I cannot go add more pages over here. So okay, let me do this quickly here. CP by R into PdV plus CV by R into PdP. So I can write this as CP by R into PdV equals to minus CV by R into PdP, or Cp into PdV is equals to negative Cv into V into dP. Okay, so or Cp dV by V equals to negative Cv dP by P. Okay, now let's integrate this. Let me write this over the next page. Cp dv by v equal to Cv dp by p, negative Cv dp by p. Okay, so we'll integrate this in both sides. V1 to V2. Oops. Sorry, problem. Okay, so I'm sorry for the disturbance in the board. Sorry. So what I was doing, this will be will integrating this v1 to v2 and then p1 to p2. Okay, okay, so what will be that? Cp into ln v2 by v1, that is equals to Cv ln negative Cv ln p2 by p1. Okay, or Cp by Cv ln v2 by v1, that is equals to negative ln p2 by p1. Or Cp by Cv, we know this is equals to gamma ln v2 by v1. This is equals to ln, let's reverse this, p1 by p2 because we are cancelling this negative sign. Okay, or ln p1 by p2, this is equals to ln v2 by v1 to the power gamma. Okay, so we are cancelling the ln in both sides. Or p1 by p2 equals to v2 by v1 to the power gamma. So this is the relation between p and v, or p1 v1 to the power gamma is equals to p2 v2 to the power gamma, or pv to the power gamma is equals to constant. So this is the relation between p and v for a reversible adiabatic process of an ideal gas. So I have derived the relation between T and V and also derived the relation between P and V. Next, in my next video, I'll derive the relation between T and P in case of reversible adiabatic process of an ideal gas. And I'll continue my discussion on thermodynamics. I will derive more mathematical formulas as I continue my discussions. So for now, bye bye, and please do watch my thermodynamics series if you want to know the details on thermodynamics. And please do watch my previous videos for better understanding, and do watch my next videos to know more. Okay, so bye bye for today, and please like, share, and subscribe my channel. So bye for today.